Think of the last time you misplaced your phone in your room and couldn't find it even after seemingly searching everywhere. Later, you might have discovered your phone was right under your pillow or next to a pile of books. That's an error of omission. You missed what was right in front of you. In statistics, the power of a test deals with a similar concept. When we make errors by failing to detect an effect that's truly present, it's often due to the lack of power in our test. Although hypothesis testing helps us determine whether or not to believe certain claims, it's not a perfect system. It has some limitations. In hypothesis testing, we make two types of errors, conveniently named as type 1 and type 2. A type 1 error occurs when we reject a null hypothesis that is actually true. This would be like sounding a false alarm. A type 2 error occurs when we fail to reject a null hypothesis that is actually false. This would be like missing the actual alarm. Hence, the power of a test specifically addresses this second type of error. It's the probability that we correctly reject the null hypothesis given that the null hypothesis is actually false. Essentially, it measures our test's ability to detect a true effect. Think of it like a metal detector at the beach. The more powerful it is, the better its chances of detecting a buried treasure. A weak detector might just beep for larger objects and miss out on smaller treasures. In our statistical tests, the power represents the capability of our test to pick up on these significant effects given that they actually exist. There are four main determinants in the power of our test. Firstly, the effect size. The larger the difference between our null hypothesis value and the true value, the easier it becomes to detect this difference. Secondly, the sample size. A larger sample generally gives us more information and thus increases the power of our test. Thirdly, the significance level. Setting a stricter significance level, like 1% instead of 5%, reduces the power because it makes our test more conservative. Lastly, the variability in the data. More variability, or noise in the data, makes it more difficult to detect a true effect. In my previous videos on hypothesis testing and confidence intervals, we looked at an example situation about the effect of marriage on wages. I highly recommend checking them out to understand the backbone of hypothesis testing. Hope you enjoy them. From this example, here's another code I made in Wolfram Mathematica to delve further into the power of a test. The code may be quite lengthy, but it makes the concept fully interactive for your learning. On screen, you will see a dynamic plot I created. This displays how changes in any of the factors involved in the calculation can influence the power of our test. Essentially, the power of a test is calculated in the following way. First, find the critical value for rejecting your null hypothesis. Since the alternative hypothesis is two-sided, this critical value will be both positive and negative. Then, use your null hypothesis and the standard error of the coefficient estimate to find the lower and upper bound values of the coefficient estimate, outside of which you would reject the null hypothesis. Now, convert these lower and upper bounds into a standard normal distribution to find the cumulative distribution of the true hypothesis to the left of the lower bound and to the right of the upper bound. Lastly, add these two, and this is the power of the test. Using these sliders, you can change the value of these variables and instantly see how the power changes. The power is hereby represented as the purple shaded area. For instance, the greater difference between the null hypothesis and the true value will give a greater power to the test. Similarly, the less difference between the null hypothesis and the true value, the lower the power will be, all the way until power is equal to the significance level. A larger standard error, indicating more variability in the data, leads to lower power, up to the point where power is roughly equal to the significance level. The non-shaded area within the true distribution of blue color represents our type 2 error rate. That is, the probability of failing to reject a null hypothesis that is actually false. As the power increases, the type 2 error rate decreases, and vice versa. Therefore, the type 2 error rate is equal to 1 minus the power of the test. Imagine you're researching a new drug and want to determine if it's effective. If your test is low in power, you might incorrectly conclude that the drug isn't effective when it actually is. This could deprive patients of a potentially beneficial treatment. Conversely, ensuring your test is powerful can aid in making more confident decisions based on your research. The stakes are high, so understanding and optimizing for power is crucial. To explore independently and gain further insights, you can use this code on my website through the link in the video description below. Remember, just like with hypothesis testing and confidence intervals, the power of a test is all about balance. We must juggle between being too lenient or too strict, potentially overlooking effects or finding effects that are not there. Hence, it's important to be very careful. The journey into the world of statistics is filled with many fascinating chapters. Each concept, like the power of a test, adds a new layer to our understanding, for an entire universe of data to be explored.